Welcome everybody. My name is Jedrzej Potoniec. I'm with Poznan University of Technology in Poznan, Poland. And today I will be presenting a joint work with my former master student, Dariusz Max Adamski, with the title Reasonable Embeddings, Learning Concept Embeddings with a Transferable Neural Reasoner. And this work is basically a summary of the master thesis of Dariusz, and it was also recently published as a full paper in the Semantic Web Journal. So the talk will consist of, let's say, 4 main points. I will start with some motivation for the research and preliminaries to give you the necessary background. Then I will tell you about the internal details of reasonable embeddings of our solution, and then I will show you the results of the experimental evaluation, and finally I will summarize and conclude the talk. So the our overall hypothesis was that concepts from different knowledge bases expressed in the ALSC description logic can be represented in a shared embedding space and with a topology that lends itself to approximate reasoning by classified based on a neural network and suitable for classifying entailments, whether they hold or not, or in other words, whether any given query is entailed by a knowledge base or not. And the most important part here is that the embedding space is shared between multiple knowledge bases. The idea is that there is a single neural reasoner which is employed by multiple knowledge bases, of course, represented in a suitable manner. And well, this is more or less how would logic work, but let's discuss what ALSC knowledge bases consists of. So the ALSC description logic consists of top and bottom concepts that correspond respectively to the whole domain or universe of discourse and to an empty set. There are also intersection and union available, so one could construct a concept being an intersection or a union of two concepts, and those operators, of course, correspond to set intersection and set union over the interpretations of those concepts. There is a complement or negation available corresponding, and the concept not C corresponds to all the elements of the universe of discourse except for the items in the concept C itself. And finally, there is an existential restriction and a universal restriction, and denoted by respectively the quantifier exists and the quantifier for all, are a role under the quantifier and a concept. And those two correspond to a bit more complicated expressions. I will not go here into the details as they are not of utmost importance for the talk. So there are only a few operators in the ALSC description logic, and there is an algorithm which lets you to which enables you to decide whether any given query consisting of two concepts, let's say C and D, whether C is a subclass of D given this or that knowledge base. The algorithm is there, it is, and it has all the necessary properties from the logical point of view. It is so it is sound, it is complete, it is terminating, it is even reasonably efficient, at least in typical cases. So one could ask why if we already have this algorithm and it more or less works, why to try to employ neural networks in it. So one thing for me was that I was very curious if it is possible to mimic logic in neural networks to this extent that the operators, the reasoning algorithm, that they are shared between multiple knowledge bases. And the other nice property which we aimed to achieve, and it seems that we managed to, was that we wanted to be able to compute embeddings of complex concepts such as a conjunction from the embeddings of the arguments. So for example, given two embeddings for two concepts, again C and D, we can compute an embedding of their conjunction C and D. We don't need to train this embedding. Once the embeddings for C and D are trained, the embedding for their conjunct, for their union, etc., is already, let's say, fixed and can be computed. And this computing property is in theory infinite, in the same sense as one can apply logical operators again and again and again, getting more and more complex expressions in logic. So that is the motivation, but it must be underlined that there was no goal in this work in the sense that we don't have any particular application in mind. It is a typical case of fundamental research. We just wanted to see if it is possible to construct such a system. However, one might envision applications like, for example, hot swapping ontologies or extending ontologies, or rather their neural counterparts, so the embeddings, without the necessity of retraining everything from scratch. So the architecture of the solution consists of the main part is the neural reasoner, and the neural reasoner itself consists of two subparts. Reasoner head, which is shared between all the knowledge bases, and it consists neural operators for conjunction, for negation, the embeddings for top and bottom concepts, since they are also shared between knowledge bases, and the, let's say, the core, so the neural operator, the neural network for deciding whether two concepts, or rather two embeddings of two concepts are in one is a subclass of the other. Then for every considered knowledge base, there is also an embedding layer. The embeddings are separate for every knowledge base, and they live in the same embedding space in this sense that they share the reasoner head, they share the operators, so then they need to share some properties. However, as far as we know, they are not comparable between different knowledge bases. So for example, it is a typical example for word embeddings to compute distances between them, and do analogical reasoning and stuff like that. So in here, I guess it is also possible, but within a single knowledge base. The embeddings, the distance between embeddings from different knowledge bases is not necessarily properly defined. So this is the core system and the core of our solution, the neural reasoner. And in machine learning terms, the neural reasoner, or more precisely, this part for deciding whether a subsumption holds, is a binary classifier. The classifier gets two embeddings as its input and outputs a binary label or a probability of the given entailment holding with respect to the knowledge base which the embeddings originated from. And the whole system was trained by using a set of knowledge bases and set of queries of some complex expression, subclass of another complex expression, labeled with a real logical semantic reasoner. In our case, we used Fact++, but of course, any other tool like Pellet or Hermit or whatever you want to use could be employed here. And this semantic reasoner generated true labels for us, either positive, meaning that given query follows from the knowledge base or is entailed by the knowledge base, or zero if it couldn't be, if it didn't follow, basically. And this way, we obtained a very nice thing in the world of machine learning, namely a data set which was noise-free. Every label was necessarily correct since it was generated by a logical reasoner, which, of course, if implemented correctly, and that's what we assumed about Fact++, doesn't make any mistakes. Using those labels, we, of course, then execute a typical training with computing loss and optimizing weights, etc. So that's the overview. And now let's drill down into the details of the neural reasoner. So the atomic concepts are represented as simply as vectors, which are optimized or learned during the training of the neural reasoner. So we represent in the slides, the embeddings are denoted by H with the knowledge base name K in the subscript, and AE here stands for some atomic concept, so a concept which is not a complex concept. Of course, top and bottom stand for respectively the top concept and the bottom concept, and those two embeddings are shared between all ontologies, but similarly to the atomic concept, they are optimized during the training. So there is no procedure like SIBO, for example, or skipgram, which is common for word vectors. Those embeddings are simply optimized in along with the whole system. And we start with to get something more complex. We have the negation operator, for example, which is simply a linear layer. So it gets a linear neural network. It gets an embedding of a concept as its input, and it outputs an embedding of the negation of the concept. And in our experiments, we fixed the embedding size to be 10. So the vectors consists of 10 numbers. Those embeddings are quite small, but the ontologies we used, to the knowledge base we used, were also relatively small. I mean, if you, for example, compare them with Word, with text, corpora, and those are very, very small ontologies. So that's why we choose to use much smaller embedding size that it is typically used in text processing. And there is no activation function in the linear in this neural network. It is simply a linear layer to enable the network to behave in such a way that if we pass this embedding as the input of the network, it should, at least in theory, generate back the original embedding. With an activation function, this of course would be impossible, or at the very least much more difficult. So conjunction and disjunction were realized jointly. We have again a single layer, a single linear layer to represent the neural counterpart for the conjunction, and it outputs an embedding of the size of 10 for C and D, given as its input two embeddings for the concept C and for the concept D. We do a small trick here. The layer itself gets not only the embeddings themselves, here denoted by U and V, but also their outer product. So we transform two embeddings, 10 values in each, into a vector consisting of those two embeddings, that's 20 values, and their outer product, which consists with another 100 values. And since we already, at this point, we already have negation and conjunction, union is simply realized by combining them using the Morgan's law, as indicated here in the bottom of the slide. And such a combination is possible because those neural networks I'm just describing, they are present, so they basically form parts of a recurrent neural network. Recursive neural network, meaning that in a similar way as there are grammars, for example. And those reasonable embeddings, they are only concerned with roles and concepts. They don't go into the level of individuals. And this is because concepts are sets and consisting of individuals, and the roles then typically link individuals. That would be very hard to include in this embedding space. Instead, we decided to concentrate only on roles and concepts, and for every role, we train a separate neural network, a separate, again, linear layer, which basically represents the existential quantifier for this particular role. And again, universal quantifier is achieved by using the existential quantifier and negation, again using the Morgan's law. So that is more or less what I just said again. So the embeddings for roles are basically weights, neural networks weights, rather than living in the same space as the concepts. The reasoner head, so the main reasoning component consists of a bit more complex neural network getting two embeddings as its input. The interaction map is computed, so the outer product, a hidden layer consisting of 16 neurons and the ILU activation function, and then a single neuron as being the outputting the probability. And the training regime consisted of two steps. So first, the reasoner head and the embeddings for multiple ontologies are trained jointly. Then the reasoner head is frozen, and one can reuse it again and again. And if one wants to use a new ontology, a new knowledge base, one needs to train the embeddings for the reasoner head. Sorry, for only the embeddings for this knowledge base without even touching the reasoner head. So in our experiments, we used synthetic knowledge bases for training the reasoner head, and for some preliminary testing, the knowledge bases, there were 60 knowledge bases in total. They had around 100 atomic concepts between 1 and 5 roles and around 200 actions in the knowledge base and 2,000 queries per knowledge base. Only around 1/5 was positive. And on the synthetic data, the trained reasoner clearly outperformed a random reasoner, so reasoner which was only initialized and not trained. And the trained reasoner achieved almost perfect AUC ROC even on knowledge bases it didn't see during the training. On a set of real-world ontologies, a reasoner which didn't see those ontologies during the training achieved AUC ROC are almost 98%. If we let the reasoner to be trained along with those with the embeddings for those ontologies, the score was of course even higher. And if we didn't train the reasoner at all, the score was much lower. And since there are only around 20% of positive queries in the set, this basically is very it doesn't work, this frozen reasoner. The pre-trained reasoner was the what we wanted to achieve, and it worked reasonably well. So of course the experimental results are very nice and they look very good, but there are of course some limitations. So we currently work on showing the limitations, the detailed limitations, but preliminary results indicate that it cannot really handle subsumptions that are computationally expensive, and ALC is much more expressive than neural networks, so that is not a huge surprise. And it seems that it also cannot handle very complex expressions in this sense, that expressions that require long proofs. So we have two small papers. The second one will be presented on the topic, and the second one will be presented during the NESI workshop in 2 months' time in Siena. So to conclude, the reasonable embeddings enable reasoning in the latent space, and the neural reasoner is transferable between multiple knowledge bases, and it shapes the latent space. Since the frozen reasoner didn't work at all, the experimental results are very high, even though the architecture is relatively simple and the embeddings are relatively small. But of course, there are limitations, both theoretical and practical. So thank you for your attention, and I'll be happy to answer your questions. So it seems that there are none currently. So I hope that you have enjoyed the talk. As I mentioned earlier, there is the paper is accepted in the Semantic Web Journal, so you can. This is an open access journal, so you can see the paper, and the presentation from my talk is of course available in Zenodo. And if you have any questions after the session, maybe please don't hesitate to reach to me by email. And once again, thank you for attending the presentation.